This is another 2023 number challenge. The problem here is to try to find the first 6 digits of the big number 2023 raised to 2023rd power. Now we want to first review for a big integer n, how many digits does n have? If n has k digits, then the minimum value it have is going to be 1 followed by k minus 1 zeros. The maximum value n has would be a bunch of 9s. How many of them? K of them. That is 10 to the k's power minus 1. So that is, if a number n has k digits, we know that n must be in this range. Okay? So here, if we take log base 10 logarithm, it's easier to manipulate. Okay? So let's do that. Let's take a logarithm here. Alright, and then we're going to plus 1 for this inequality. We get this. Notice here, n is an integer, is a big integer. K is also an integer representing number of digits. But when we take a logarithm, it's no longer integer, right? But k, this quantity here in between is between k and k plus 1, right? So it's sandwiched between these two boundaries here. So that is, if you write in another format, it's going to be k equal the integer part of log n plus 1. Yeah, so there's a plus 1 here. So that's good. So what's our n here? Our n is 2023 raised to 2023rd power. So in order to find the number of digits it has, we need to take a logarithm, right? So log n here, if you do a calculation here, of course this logarithm is base 10, right? So if you plug in into a calculator, you get this. This is about 6688. So the k would be the integer part of this plus 1. So that is 6689 digits. Okay. So our original problem, however, is not to find out how many digits. Rather, we want to find the leading 6 digits. Yeah. So we want to find the first 6 digits of that. So how do we do that? Let's do some analysis from the earlier logarithm equation here. Okay. So let's go back. So we know this k here is 6689, and this d1 representing each individual digits. Of course, any digits here is going to be 0 to 9. The leading one, however, is non-zero. Is going to be at least 1, right? And let's assume that is the case. And we want to find the first 6 digits. That is d1 through d6. We want to find each of them. Yeah. So if they represent an integer m here is the digits, the first 6 digits. That will be an integer, 6-digit integer here. Yeah. So if we know the value of m, then this whole quantity here is approximately, if we ignore all the values afterwards, right? So that's gonna be an approximation. Yeah. So of course, what is m? M is 6-digit integer. M is integer value here. Now if we further use a decimal here, yeah, between d1 and d2, if I add a decimal, that is, if x is something here, that is d1 is some single digit number, so x would be some fraction here in between 1 and maybe 10, right? Because the d1 is everything is a digit here, is from 1 to 9. So if that is the case, what is m? M would be x times 10 to the 5th power, right? So plug into the equation here, what do we get is this. Okay, so this is just nothing but replace x times 10 to the 5th power into this equation, and then this 10 to the 5th plus k minus 6 would be k minus 1, right? So you have this. Now this time you take a logarithm. Let's do that. The left hand side, earlier we know that is 6688 plus some fraction part, and here k, what is k? 6689. So that is, you have 6688 here, right? And this 68 would cancel. What you get is this. Okay, this is inconsistent with what we have earlier, right? We know the x here is some number greater than 1, smaller than 10, right? So the logarithm base 10 would make the value less than 1, greater than 0. Indeed, the left hand side is 0 point something. So what is x? We need to find the x, because if we do, then we know m. M is just this digit here, and we need to find x with good precision. We at least we want to be correct in the first this 6 digits, right? If you go back to x, that would mean we have to be very close to the true value of x, such that log x equal to this. So here we're going to resort on what is called Newton's method in finding the root. What is the root? We try to solve an equation log base 10 x equal to this quantity here, and we try to find x. If we get x with good precision, then we will know m. That's the strategy. So what is Newton's method? Let's have a review. Let's review Newton's method, which is a common numerical method in root finding for a smooth function that is differentiable. So here, the idea is that you're going to start with x naught, which is some estimate of the root, and you're going to iteratively updating the x. Now x1, which is the next estimate, is going to be calculated by this formula here. In general, for xn, and xn plus 1 is related to this term here. The difference here is f, the value, the function value, over the derivative value at that particular position. What is the geometric meaning of that? So there's a diagram here, illustrate the iterative algorithm here. So here, the distance here, the difference between the two, the ratio of the function value f xn versus the derivative here, which is the slope. This is a tangent line. The red line is a tangent line, and the update is bringing this xm closer to the real root here. The intersection point will be the real root. Xm plus 1 will be a better estimate of it. Of course, usually for the iterative algorithm, we want to measure the rate of convergence. This is how fast can you go towards the real root. There may be other methods here, but here we only interested in the Newton's method. Okay, so here there's an illustration. So you have initial value here, and then gradually you're gonna have update next time, and then you go here tangent line, and then you go to here, and then this xn oscillate between left and right hand side of the real root, and it's getting closer and closer. Okay, this is just a animation of that from the Wikipedia page. Let's go back to our own problem. Remember, our problem is actually log base 10. Okay, let's go back to the real problem here. Let's go back to our original problem. We try to find x using Newton's method. Now, for this case, we need to solve the equation log base 10 x equal a, where a is given, using Newton's method. Now, what is function here? Function would be this, the derivative. Notice that this log base 10, so derivative would have this constant here. This is natural log here. Okay, so plug in the iterative formula for Newton's method. We're gonna have this. This would be the nth iteration, and this would be the update for the next iteration, right? Plug in the value for f and f prime, the derivative. We got this formula here, right? So that would be the recurrence relation in the Newton's method. Try to find x. Now, what about the initial value here? Now, notice that for x lot, we try to have a good estimate of the initial value. Now, notice that this is 0 dot something, so x would be 1 to 9. Yeah. So and since this is 0, 0, 2, so it looks like it's this is log base 10. So x probably is smaller than 2. It's between 1 and 2. So let's put maybe 1.25 as the initial value. With that, I run the Newton's method iteration, and within a few iteration steps, for example, n equals 7, this value is getting close enough. Alright, so the leading value here looks like is 107070. Yeah, we look for the first 6 digits, right? So that would be it. 107070 would be the leading values here. Now indeed, when I actually use big number calculator to calculate this, the leading value is indeed 107070. Okay. Now there may be another method we're going to introduce. This turns out to be simpler than the Newton's method, but would require more computation. These days computation is easy because we have powerful computer. So let's kind of brute force way. So the analysis is that in order to figure out the first number here, for example 6 digit, what you want to do, or the first 7 digit whatsoever, what you want to do is maybe try to enumerate from the smallest possible value to the bigger value until the logarithm, however, the logarithm, because the leading logarithm is going to be matters here, cross over whatever the logarithm of this target value. Yeah, if you take log, you have the target. If you take a log here as this number, for example, if I got 5 number right, as this number getting bigger than d6, the logarithm, the leading digit would be bigger than the target value. Okay, so kind of the Python code here, and we try to find the first 7 digit, for example, of this here. And what we do is, this is the target value, this is the fraction part, right, minus 6688. And let's say we're gonna use, because since we try to find 7 digit, we're gonna use 8 digit here and take a logarithm here. Now this is logarithm, yeah, so it's logarithm because this is like 8 digits, so minus 7 would be greater than the fraction part. When the first crossover, that would be the value. Now notice that since this is 76 is bigger, so the value should be 75. Okay, and when we run, the actual value is indeed this digit is 5. So we got pretty much not only the first 7 digit, but also the first 8 digit, because from the fact that you have 6, this is the first time where you cross the threshold of the target value here. And what we can do is we can conclude that the first 8 digit is 10707075, and in reality that's 75. Okay, so that's interesting. Now we have some other number challenges. Please check out other values. I provide the link for the playlist in the description of this video. In the meantime, please like, share and subscribe to the channel.